Hey everybody, here's part 2 of our types of energy with work and energy here. So we understand that work is force times distance, and the energy associated with that is measured in joules. So, work is force times time, or force times distance. That is in joules, or a Newton times meter, okay? And then, so if we're talking about energy, there's got to be different types of energy. So we're talking about mechanical, thermal, electrical, nuclear, chemical, etc. But what we do, when we do work, we convert it from one form to another. We'll mostly be concerned with potential and kinetic energy, which fall under mechanical energy for the most part. This is what we'll be dealing with. So let's first talk about potential energy. Potential energy is basically stored energy, right? It has the potential to do something. What we're going to be mostly dealing with is gravitational potential energy. And so you'll see it written like this. It'll be either U sub G or PE grav or E sub P. There's lots of different ways to do that, but we'll go ahead and just call it potential energy. Sometimes we'll use a G, sometimes we won't. But it's going to be mass times gravity times height, okay? And I think we've all kind of remember this from maybe 8th grade, I think, if you went here. But what we do here is we have this mass of the object, we have the gravitational pull, obviously, and the height, well, the height is relative to some point here, right? The higher the object goes, the more potential energy it has, only if the reference point gets below it, right? So if here's my 0 point here, if I raise up the object a distance h, it now has some time of energy. If I consider this my 0 point, that blue line now, all of a sudden my height is now 0, so from that blue line's point of view, I have no energy, there's no height to it. The other thing we have is kinetic energy, and we call that the energy of motion. And it's simple, it's pretty straightforward. We have Ke or E sub K. I usually write Ke. So we have kinetic energy is 1/2 mv squared. There's a derivation, we can work on that. But for the most part, we basically have the mass of the object and then the velocity object. Once again, these are all measured in joules. So over here we have both the potential energy and the kinetic energy, and those will be measured in joules. So we have a couple of different ways we can describe this. First thing we'll do, we'll have example 6 here, the work energy theorem for net force. And what we have here is work is equal to the force times the distance of the object. Well, work is equal to the change in kinetic energy of the object. So that delta Ke is basically 1/2 mvf squared, the final velocity, minus 1/2 v naught squared. And so we can write it again with factoring the constant and the mass. So vf squared minus v naught squared. There's a couple of different ways to write that. But the work done is the change in energy. So here we have an example, a car accelerating. It has an initial velocity and then a final velocity over a certain distance. So determine the average net force on that car. So let's see, we can start off with our equation. Work equals change in kinetic energy. We know that the change in kinetic energy is equal to the net force times distance. And if we're looking for the net force, then it goes to follow delta K divided by D is the net force, right? That is what the math tells us. Let me fix my sigma here. And then we can fill some stuff in. We know that the delta Ke over D would turn into 1/2 m, and then we have this delta V squared inside this divided by the distance still. And from there, we can plug everything in. There's the 1/2. The mass is that 1270 number. The final velocity, so what I'm doing is I'm just looking at the delta V and using this VF squared minus VI squared, or V naught squared. So that's where this 25 squared minus 15 squared comes from, divided by that distance of 75 meters. So we should get a net force of about 3390 newtons. So that was the net force that provided the work to change the velocity from the 15 to the 25. Another way to look at this is to look at a graph, and we know the graph is demonstrating a force versus distance. And so we have a couple different questions. One, what's the total amount of work done? And then the last one here is the final speed of the object. So the first thing I want to do is I'm going to break this apart into different areas. So this is area 1. Then we have this big guy here. We'll call this area 2. And then this third area, this triangle right here, we'll call that area 3. And what we can know here is the area of a force versus distance is work. So the area of force versus different distance is work. So the area of the first one, that's a triangle. So 1/2 base times height, and that gives me 20 joules. For the second one, it's a square or rectangle-ish looking thing. And so this is 80 joules. And then the last one, the third area, is another triangle that would give me 40 joules there. So for the total amount of work done, all we're going to do is we're going to add all of these areas together to get a total area of 140 joules. So that would be the total amount of work done on this object. The final speed of the object is we can do that the same kind of way. So for part B, we know that work is a change in kinetic energy. And we know that the work, we can write it this way, is 1/2 mvf squared minus 1/2 mvi squared. Or initial, sorry, here's my O. And what we know happens here is that there's no initial velocity, right? Over here at the beginning of the graph, it's at 0, right? So there's nothing happening yet. So with a little bit of math, we get the final velocity is equal to the square root of 2 work over m. When you plug everything in, you get a final velocity of about 4.3 meters per second. So a couple of different ways to solve these kinds of questions. So the last thing we're going to talk about is this conservation of energy idea. So to summarize our work-energy relationships, we have the total work, call that work subtotal, is equal to the change in the energy, the total energy of the system. And right now we know it's the force, the applied force times distance. We have the change in kinetic energy, which is the net force times the distance. And then we have a change in energy due to heat, and that's just going to be the force of friction times distance. That's typically where we talk about friction and heat. So we know about the law of conservation. We know that if something is conserved, then it stays the same. And we know that energy cannot be created or destroyed, only changed from one form to another. So what we know that if there's only conservative forces are active, so conservative being the key word there, the total change is going to be equal to 0. So what that means is we have a way to write that equation-wise. We have the kinetic energy initial of the system plus the potential energy is equal to the final kinetic energy plus the final potential energy. So if the total change is zero, what happens is the change in kinetic energy plus the change in the potential energy ends up being zero. Another way to write that math-wise is change in kinetic energy is negative delta change in the potential energy. So a quick example of that is a roller coaster. And so we have a peak hill that's 55 above ground, and then that's 30, so we can see a change in height. So the sketch of that looks something like this. We have the top hill and then the bottom hill. We know the first one is about 55 and the second one's about 30. And we know that the difference between this is 25 meters, right? There's that delta H in there. So from this point here to this point here, there is a change in energy. There's a change in potential energy occurring there. So if we use our total initial and final energy equation, looks something kind of like this. The initial kinetic energy plus the initial potential energy is equal to the final kinetic plus the final potential. What we're assuming is up here at the top, he's not moving. He's going to start at rest. That's typically how our questions go, right? So if the initial velocity here is zero, that means there's no kinetic energy at the top. Over here, we're assuming that this is the level that we're looking at. So the height here ends up being zero. So there's zero potential energy at the end of this. So what happens is we have the mgh initial over here on the left and the 1/2 mv squared over there on the right. Notice the masses end up canceling. Since we were looking for how fast the car is traveling, we solve for the velocity. So the final velocity ends up being 2ghi, take the radical, plug all that stuff in. Remember, this 25 is from that difference in the height. So we get a final velocity of about 22.1 meters per second. So once again, the change in energy thing is going to be a big deal. Total energy, this is going to how we use our conservation laws, and understanding that work is the force times distance, and depending on what we're looking for, if we're looking for the change in kinetic energy or the work total, is going to be dependent on either the applied force or the net force. All right, let me know if you have any questions. Thanks for watching. Bye.